Okay guys, this is the first video of Chapter 6 where we will be discussing the electronic structure of atoms and the structure of the periodic table of elements. In this first section we are going to discuss electromagnetic energy, which is important and helpful for us to understand how atoms work. And so we're going to start there. And in this video, we will talk about some of the basic features of electromagnetic waves. We'll talk about light and the electromagnetic spectrum. And then we're going to do a few calculations involving the frequency and wavelength of light. And then we'll get to a couple of other topics from this section in a future video. To start off this chapter, I wanted to point out a distinction between classical physics, which came before, basically it's anything before the beginning of the 20th century, and modern physics, which is anything essentially after the start of the 20th century. Classical physics had established the laws that essentially governed macroscopic motion. For example, Newton's laws of motion. Likewise, electromagnetic waves were understood using Maxwell's theory. And then topics like thermodynamics and the beginnings of chemistry were able to explain much of the material world. And the processes that it undergoes. One of the underlying assumptions in this classical physics is that energy is a continuous function. So in the macroscopic domain of classical physics, energy is a continuous quantity. And there was no reason to really question that assertion. However, experiments that started in the late 19th century and we'll talk about a few of those in this lecture series, revealed discrepancies with classical physics. And so these experimental discrepancies, which were brought about by new technology, essentially, ultimately led to new theories in what we call modern physics. These, among others, these are referred to as quantum mechanical effects, which refer to phenomena that are associated with the particle-wave duality of both light and, importantly, microscopic matter. So things like electrons and individual atoms and perhaps also individual molecules. They exhibit physics that is essentially different from macroscopic objects. And so ultimately, in the end, what you see in the microscopic domain is that energy is not a continuous quantity. It is discretized, and we call it quantized. That's what the word quantum means. It means a discrete bundle. Since the wave-like character of matter is important for understanding atoms, we need to have a bit of a discussion about waves. And so even from the classical perspective, waves were well known. They referred, a wave is some type of repetitive oscillation of a medium. For example, the surface of an ocean wave, or in acoustic waves, the air pressure, and in electromagnetic waves, you're talking about the oscillation of an electric field and a magnetic field. Something that's oscillating and that propagates through space as a function of time. That's what a wave is. So it's an oscillation that propagates through space as a function of time. We can talk about the very basic anatomy of a wave. So a wave has an amplitude. This refers to the maximum magnitude of whatever it is that's oscillating. For example, in a surface ocean wave, the height of the wave above sea level would be the amplitude of the wave. And you can have crests and troughs, and then there's a part of the wave called a node. Here, I'll go ahead and show you that on the next slide here. Here we're just looking at a few simple sine waves. And so you've got some baseline 0 amplitude here that runs through the middle, and you see that you have these different crests and then what are called troughs, and then places where the wave equals 0 amplitude. Those are called the nodes of the wave. We also have ways of quantitatively characterizing waves. The wavelength, which is represented by the lowercase Greek letter lambda, refers to the distance between equal parts on a wave, and so it's measured in units of meters or some other scaled distance. Also, there's a quantity called the frequency of the wave, which is represented by the Greek letter lowercase nu. That refers to the number of wave cycles that pass by per second. So let's turn back to these pictures to try to understand the wavelength and frequency of a wave. So just imagine that this wave here, we're just looking at it while it's frozen in time, and then we would measure the distance between two equivalent points of the wave. And so that distance is called the wavelength. The frequency, on the other hand, you need to allow the wave to move in time. And so what I will ask you to do is to imagine that you're standing at a beach and watching the waves come in. And let's suppose that these waves are well organized and all have the same wavelength. What you would do would be to stand still and count the number of waves that pass by you in a given amount of time. And so you would take that number of waves that pass by you, let's say in 2 minutes or something like that, count the number of waves that pass by you in 2 minutes, and then divide that number by the time. So what you wind up with is something like wave cycles, that is wavelengths per unit time. And so the units that are used for the frequency of a wave are reciprocal seconds. And this is also called the hertz. These pictures here are showing that there is a relationship between wavelength and the frequency. So assuming that the waves have the same speed, what you can look here is how many wavelengths can pass through this distance in a given. Let's assume that the wave passes is moving so fast that it goes this far in 1 second. You would then count the number of cycles that pass by. So there's 1, 2, 3 cycles for this wave in a given second, and so we would say that that's 3 hertz. Here we have a wave that's traveling at the same speed but has a shorter wavelength. And so in that same distance traveled by the wave in 1 second, you have 1, 2, 3, 4, 5, 6 cycles. So the frequency is then larger. It's 6 cycles per second. Here the wavelength's even smaller, and you can count out 12 cycles in a second. So that has an even higher frequency. This figure here just illustrates the amplitude effect. Okay, so some waves have a larger amplitude than others. And classically speaking, the amplitude of the wave is what determines the energy of the wave. You can think of that in terms of ocean waves. So a 100-foot wave sure does have a lot more energy than a 3-foot wave, right? In terms of sound, a very large difference in air pressure, for example, if this represents the air pressure at a particular point, a very large change in the air pressure refers to a very loud sound with a lot of energy, compared to a small, minute change in the air pressure, which would correspond to a soft, lower energy sound. Here we are quantifying the relationship between the wavelength and frequency of light. They are inversely proportional to one another. We need to introduce the speed of the wave. You can either use the symbol v Or when you're talking about light, you typically use the symbol c to represent the speed of a light wave. And so the speed has units of meters per second, and the speed of a wave is equal to the wavelength times the frequency. And I just wanted to briefly show you the units there. So if you take wavelength, which has units of meters, and frequency, which has units of cycles per second, you see that the units, when you combine them, are meters per second. Okay. Now this is a very important formula that you need to be able to work with. You want to have it memorized, and then you also want to be able to rearrange it so that given the frequency of light and then it's the speed of light, then you can calculate lambda, or given the wavelength and the speed of light, you can calculate the frequency. And that's what the examples that we'll have are in a couple of slides. So I wanted to talk a little bit about electromagnetic waves and the electromagnetic spectrum. So light consists of an oscillating electric and magnetic field that propagates in time. So there's a wavelength for light, a frequency for light, and then a speed of light. For all frequencies and all wavelengths of light, the speed of light in a vacuum is the same. So this is sort of the constant speed limit of the universe, as it's sometimes called. The speed of light is 2.998 times 10 to the 8th meters per second. We will usually round this to 3.00 times 10 to the 8th meters per second. And what you're looking at here down below is a representation of the different classifications of electromagnetic waves. So the light that we see all around us is actually a very narrow band of the electromagnetic spectrum. It ranges from red all the way down to violet, and it composes just a very small portion of the electromagnetic spectrum. At longer wavelengths, we have infrared radiation. Beyond that, we have microwave radiation. And then beyond that, in terms of longer wavelengths, we have radio waves. If you go to smaller wavelengths than visible light, we have what's called the ultraviolet range. Smaller still are X-rays, and then smaller than that are gamma rays. Most chemistry makes use of light between X-rays and, in some cases, in certain types of technology, radio waves as well. So most of chemistry is over on this side of the electromagnetic spectrum. Here we're talking about what we'll find out are very high energy waves in the gamma radiation. We don't typically deal with that in chemistry. In any case, it's a good idea to know about the different regions of the electromagnetic spectrum, and you certainly need to know the inverse proportionality relationship between frequency and wavelength. So in this scale, wavelength increases this direction, but frequency increases in the opposite direction. So X-rays have a very high frequency compared to visible light. They also have a very short wavelength compared to visible light. Radio waves have a long wavelength and a short frequency, a small frequency. So here we're going to be doing some of the problems that you'll need to be able to solve, and they use this relationship here, the speed of light as it relates to the wavelength and the frequency. Here in this first example, we are given the frequency of yellow light, 5.09 times 10 to the 14th hertz. If you're familiar with, I'm sure you're familiar with street lights, so that yellowish type of street light, this is the type of light that we're talking about. Those are sodium vapor lamps, and so these this is the frequency of those types of the light that comes from those types of lamps. So we are being asked to calculate the wavelength here. So we need to rearrange this equation, c over nu, and then we can plug in the speed of light, and then we'll plug in the frequency. So this is the unit hertz, H-E-R-T-Z, and then that's equivalent to 1 over seconds. Okay, and so that's going to give us, you'll see that the 1 over seconds cancel, and that's going to leave us with the wavelength in units of meters. And so I'm getting a value of 5.89 times 10 to the minus 7 meters. It is common to express this in units of nanometers, and so that would be 589 nanometers. Very often visible light is expressed, the wavelength most commonly is expressed in terms of nanometers. Part B is the same. Okay, so it's solved in exactly the same way. You just need to plug in a different value for the frequency. So I will let you do that one on your own. Part C is the opposite. We are being asked to calculate the frequency for a particular wavelength. Okay, so we need to rearrange the equation in a different way. We need to solve for the frequency, which is c divided by lambda. And so in this problem, we'll take the speed of light, and then we're going to divide that by this wavelength, 408 times 10 to the minus 9 meters. We'll get that number. .35 times 10 to the 14 hertz in this case. And part D is going to be identical to that. You just need to plug in a different wavelength. One of the other interesting aspects of waves is that they are not local objects. They're not like matter in the sense that, particles and macroscopic objects, they have a definite position and speed that changes with time, and you can follow the path of an object or a particle. You can follow its trajectory in time. Okay, and so it has a definite location. However, waves are not localized to one point in space. Right? Waves extend throughout space. If you've ever flown over a large body of water that has waves, you can see that the wave, it really extends throughout space. And so we say that such an object is non-local. Waves also have a phase. That is, there is some origin of the wave in terms of its position and time. And different waves have different phases, okay? And that's important because that leads to what we call interference effects, okay? So whenever you try to take two waves that have their own phases, whenever you try to put them in the same region of space, what happens is that the amplitudes of the waves add together. They can add together constructively, which will reinforce and amplify the amplitude of the wave, or the waves can add together destructively such that the amplitudes cancel out. And you're familiar with interference patterns. I'm sure you've thrown stones into water. You see these ripples here that emanate from each stone. They emanate kind of circularly. Right? There's rings that sort of spread out across the surface of the water. But if you have two stones that strike the surface at roughly the same time, when the rings from the different ripples approach one another, you get these interesting patterns that you see here. So these are referred to as an interference pattern, where the amplitude associated with different waves are interfering with one another constructively and destructively over space. Another thing that waves can do is that they can diffract, and that's something that material objects, at least macroscopic material objects, cannot do. Whenever a wave encounters an obstacle or an opening, an aperture, that's comparable to its wavelength, it will cause the wave to bend in different ways and lead to these what we call diffraction patterns. And so here's an example where someone has shined light onto a screen that has two slits in it for the light to pass through, and then the light emerging from the two slits on the other side is then projected onto a screen behind the first screen. And what happens is that the light, under certain conditions, associated with the size and dimensions and separation of the two slits in the first screen, what happens is you get a diffraction pattern appearing on the back screen. And so you have bands where the light coming from the two holes in the screen reinforce one another, and then you'll have these dark patches where the amplitudes cancel out. Okay, so this is due to the diffraction of light in this example, and it's a characteristic of the wave-like nature of electromagnetic waves. Here's another interesting thing about waves. So waves there's multiple types of waves. Some waves are classified as traveling waves. These waves, they propagate through space. You can think of them as much like a sine function that's just moving through space, like an ocean wave does. Or you can think of, or there are what are called standing waves, and this is more relevant to, you would have encountered this if you've ever watched someone play a guitar, or if you play guitar yourself. Standing waves are waves that are confined to a region of space. And so here we have some string, okay, that's confined between two stationary posts. And if you pluck the string, you'll see that the wave sort of bounces back and forth like this. And so this is, the wave here refers to the height of the string above its equilibrium position. And then, if you just pluck the string by itself, then you get this wave here where the amplitude just oscillates up and down. If you kind of pin down the wave in the middle and then pluck it again, you can generate a wave that looks like this. It has a shorter wavelength, but it's a stable wave, and then you'll get the two sides of it bouncing back and forth. You can also create nodes at two places along the wave and create a standing wave that looks like this, and then in time this part will go down while that part goes up, and this part will go down, and it just goes back and forth like that. And you can create a whole bunch of these types of waves just by adding more and more nodes to the wave between the two boundary points. These are called standing waves or stationary waves. And what I'll draw your attention to is the fact that these different standing waves, these are the ones that are allowed. They have restricted wavelengths. So, for example, the longest wavelength that can fit between these two posts has a wavelength that's twice the distance between the posts. So here you're seeing the first half of the wave, and then you can extend the wave. You would imagine that the wave goes that way with the negative trough. This is the longest wavelength wave that can fit between the two posts. That is, and still have the ends tied down at the posts. The next shortest wavelength that fits between these two posts has a wavelength that's equal to the distance between the two posts. Okay, so if the wavelength is between this wavelength and then that wavelength, that wave would not survive along the string. Eventually it would destroy itself through destructive interference. This is the next shortest wave. And now the next shortest wave, you see the wavelength is about you can fit 1.5 wavelengths between the two posts. Okay, so we've made the wavelength shorter, but in order for the wave to survive, you have to decrease the wavelength until you get just 1.5 cycles of the wave between the two posts. No other wavelength between these two will fit. And if you keep going further, here you have exactly 2 wavelengths between the two posts. Okay, so this is the next lowest wavelength that will fit. And then you keep going like that. So these standing waves, they have restricted wavelengths. They are, in a sense, quantized. This also applies in higher dimensions. So what we're looking at here, we have some type of oscillator here, an electric oscillator that can make this round plate, it can make it vibrate in different ways. And so what you're looking at here, the metal plate is this dark brown color, and then what you are doing here is we're placing grains of sand on top of the plate as it's vibrating. And what happens is very quickly the sand will find its way into the nodes of the wave. That is, it will find its way to right here, so that it's not bouncing around so much. And so here what you're looking at are different types of standing waves for a two-dimensional medium. Here what you see, these concentric circles, these are radial nodes. So there's a node here and a node there, and there's kind of one right here. Here it's a bit more well defined, these two nodes, but you see a different pattern, and this wave has a different frequency, right? 2.4 versus 3.9 kilohertz. You can also, when you have higher dimensions, you can also introduce different types of nodes. So these two waves, they also have these radial nodes, but then they also have angular nodes that you see going around. We're going to find that atoms can do the same thing. Atoms, the waves that represent electrons in atoms, as we'll discuss, have both radial and angular nodes. And we'll look at pictures of those in future videos. The point I wanted to make here was that standing waves have restricted wavelengths. They are quantized in this sense. So we'll stop this video right here, and we'll pick up with the blackbody radiation and photoelectric effect in the next video.